good morning, everyone. Can you hear me? Okay, let's go ahead and get started. So today I'm going to pick up where I left off yesterday evening. Today I'll be talking about cutoff characterizations of some of the mechanisms that we learned about yesterday. So let's give some motivation for why we might want to do that. So cutoff characterizations. Why do we care about this? Today we're going to be looking at some of the matching mechanisms that we learned about yesterday in the context of school choice. Okay, so remember, school choice was our second motivating example from yesterday. This is where we have many-to-one matching and we have many students being assigned to each school. On top of that, there's this idea that the students are going to be strategic, but the schools are not. So we have this one-sided strategic side. The two mechanisms that we're going to focus on today are deferred acceptance and top trading cycles. If you've already forgotten what they are, that's fine. We'll briefly recap them in just a moment. But first, to preview what we're going to be doing today, we're going to go ahead and provide alternative characterizations of both of these mechanisms. In particular, we're going to characterize them in terms of something called cutoffs. And what I mean by that should become clearer once we get to the characterization. Okay, but today, a little differently to yesterday, instead of doing more of a review, today I'm going to be mostly presenting on two specific papers. The first paper is Azevedo and Leshno from 2016, and the second paper is my paper with my advisor, Jacob Leshno, from 2018, giving cutoff characterizations of these two mechanisms. And why we care about them in the context of this school is that these cutoffs can be used to define propensity scores. Okay, in particular, there's going to be some amount of randomization in school choice. And that randomization is going to induce some kind of natural quasi-experiment for us. And in order to be able to have a sort of sound empirical strategy, we need to introduce propensity scores because we're not just strictly randomizing, there's also the effects of preferences. Two simplifications we're going to make today, moving from yesterday's model to these cutoff characterizations. First, we're going to move to a large market where there's going to be lots of students. You can think of this as every college is going to admit, like, I don't know, 1,000, 2,000 students. And in addition, instead of giving a combinatorial description of the algorithms, we're going to give a non-combinatorial description. And it'll be these cutoffs. And in fact, in these large markets, you can compute these cutoffs without actually running the algorithm. That's where we're going today. But first, as I promised, let's recap what we need to remember from yesterday in order to kind of follow what's going on today. Quick check. Zoom is going well.
Everything's good.
Okay, good. Any questions, comments? Okay, let's jump in then. So recall this is our model from yesterday. We're in the school choice setting where we're going to let me make a pointer since one is out of battery. We're going to have a finite set of students, and the students are going to have strict rank ordered preferences over the schools. In addition, we have a finite set of schools. Each of those schools has some capacity or quota, QC, the number of students that it can admit. And the schools are also going to have a strict ranking over students. Yesterday, I mentioned very briefly responsive preferences. What do I mean by this? Responsive preferences mean that a school is always going to prefer admitting a more prioritized student over a less prioritized student. In other words, another way to think about it, there's no complementarity in the school's preferences. Okay, so it's not looking at the overall composition, it's just looking at the student as an individual, you know, how high is your grade or something. And the outcome that we care about is going to be an assignment of students to schools, and we want that assignment to be feasible. Okay, so that means no school can admit more students than it has space for. Okay, so that's this feasibility constraint. So the framework that I presented yesterday was first proposed in the Cutoff, and basically it's this idea that we can view school choice as a mechanism design problem. Okay? And remember, what is a mechanism? A mechanism is just going to be an algorithm, something that takes an input and produces an output, but that input could potentially be strategic, and that's what differentiates a mechanism from an algorithm. Okay? And the mechanisms we're going to think about today are deferred acceptance and top trading cycles. Okay, so here's the recap. What was deferred acceptance again? The nice thing about deferred acceptance and top trading cycles is that their names are very suggestive. So you can kind of roughly remember already. There's some kind of proposing, and the acceptance of the proposals is deferred until the end. Okay, but let's run through it again, just to jog our memories. All the students are going to propose to their favorite school. So here's Stan, Kyle, Eric, and Kenny again, all proposing to their favorite schools. Next, the schools are going to tentatively accept, not permanently, but tentatively accept the top students who have proposed to the school and reject the rest. In this case, there's too many students who applied or proposed to the Brown school. And so the Brown school is going to reject their least preferred of those two. So Kyle down here is less preferred than Kenny. And so Kyle is going to be rejected. Okay, and then to run through the rest a little faster, the students then propose to their next favorite school that hasn't rejected them. And now the yellow school has too many proposals. They have to reject their least preferred out of those, who is Eric. Eric then proposes to their next favorite school. The Brown school again has too many proposals. They have to reject their least favorite out of those, which in this case is going to be Kenny. And now Kenny proposes again to the yellow school. Kenny is the last choice of the yellow school, so he gets rejected again. And we end up with our final deferred acceptance assignment. Okay, this is kind of the combinatorial description of deferred acceptance that I gave you yesterday. Next, top trading cycles. Again, very suggestive name. We have these top pointing, and then we find cycles, and then we trade, right? Top trading cycles. So what happens? All the students are going to point to their favorite school. Same pointing as before. But now the schools also point to their one favorite student. And I mentioned yesterday that this is very important. If we point to just one school, what's going to happen is that we can pick any cycle that appears and clear. It doesn't matter which cycles we pick, doesn't matter what order we pick them, we end up at the same final assignment. If the schools were to point to multiple students, then it could be that our cycle clearing rule is going to matter, and we'll end up at different outcomes depending on which cycle we pick. So keep that in mind. That's going to be important once we start thinking about a non-combinatorial description of top trading cycles. Okay, but back to the description now. All the schools point to their top student. The students are pointing to their favorite school. And because we have this direct graph of out degree 1, we're going to have a cycle. Okay, so here's our cycle. It's a cycle of length 2. The student in the cycle gets assigned to their favorite school. Wait, I skipped. The students in the cycle are going to be assigned to their favorite school, which is the one that they're pointing to in that cycle. Okay, and then we're going through the rest quickly. Again, Stan is now assigned to the yellow school, so we remove Stan, remove a seat, and do everything again. Okay, students point to favorite school, schools point to favorite remaining student. We have now a 4th cycle, and the students in that cycle are going to be assigned to their favorite school in that cycle. So Kyle gets assigned to the Brown school, and Eric gets assigned to the yellow school. So that was one characterization of these two mechanisms we gave yesterday. Just here's the procedure. It runs in many discrete steps, just run the steps. Here's another way you could characterize these mechanisms, which we didn't fully cover yesterday. I'm not going to fully cover today, but I just want to give you a sense of it. Okay, this approach is called the axiomatic approach. What I'm going to do is I'm going to define a bunch of properties that I want my mechanism or the outcome of the mechanism to have, and ask what mechanisms are there that satisfy these properties. Okay. And so I showed you some properties yesterday. One is that the mechanism is strategy proof for the students. That means truth telling is a dominant strategy for the students. They never want to lie about the order of their preferences. Then we also had properties of the outcome, right? It could be stable, which means there's no blocking pairs, no student in school who would try to make a side deal outside of the mechanism. And also Pareto efficiency for students. There's no way for me to improve for all the students without improve for one of the students without doing worse for one of the other students. And so what I showed you yesterday is that even if we just have these three properties, there's no mechanism that can achieve all three simultaneously. Deferred acceptance and top trading cycles are both strategy proof. The other mechanism we talked about yesterday, Boston mechanism, is not strategy proof. But of these two, they're both strategy proof. One is stable and the other is Pareto efficient. And there's no mechanism that achieves all three of these properties. Okay. In fact, top trading cycles has a very nice axiomatic characterization, which is if you require strategy proofness, Pareto efficiency, and individual rationality, that's going to be enough to pin down your mechanism. It has to be top trading cycles. Okay, so I'm adding, in addition to strategy proofness and Pareto efficiency, a very weak condition, individual rationality. That's already going to say that the only mechanism you could use is top trading cycles. In fact, there's a paper that just came out this year that strengthened that to strategy proofness, pairwise Pareto efficiency, no pair can occur, and individual rationality, and that is enough to characterize top trading cycles. So there's quite a bit of theoretical literature asking this flavor of question. We have a bunch of axioms we want to satisfy. Given these axioms, what mechanisms do we end up with? But that's not going to be our approach today. Our approach today is, our driving question is there a non-combinatorial way of understanding these mechanisms that can help us think about the outcomes of large markets and also can help us perform inference? And so again, the two papers we're going to talk about are the ones on the screen here, and I believe they're also in your Dropbox if you want to pull them up for reference. They're both pretty long, so hopefully these slides can be a good starting point before reading either of those papers if you're interested. The punchline from these two papers is the following. The first one is the Azevedo-Leschno paper, and it says that the deferred acceptance outcome can be characterized using one cutoff for every school. Okay, so there's a sufficient set of statistics, just one cutoff for every school. And in fact, these cutoffs are going to solve some kind of supply-demand equation. So you can think of these cutoffs as prices for the schools. And so that's why the paper is called a supply and demand framework for two-sided matching markets. And for top trading cycles, the punchline is, again, we can use cutoffs to characterize the top trading cycles outcome, but unlike in deferred acceptance, we're going to need one cutoff for every pair of schools. Okay, so if we needed n cutoffs for deferred acceptance, we're going to need n squared for top trading cycles. So in some sense, it's not as simple as prices. There's some kind of personalized pricing or some other kind of pricing going on. And then I'll be more specific once we get there about how to think about these pairs of cycles. One moment. Again, these cutoffs, we're not going to need to run the mechanism. Well, we kind of are, but you'll see what I mean when we get there. We're going to solve something called a trade balance equation in order to find these cutoffs. Okay, there's a question in the back.
Yeah, is there a non-combinatorial way of understanding Boston?
Good question. Is there a non-combinatorial way of understanding the Boston mechanism? I thought about this for 1 minute last night, and my conclusion was it's not obvious.
There is a characterization that builds off Azevedo-Leschno's structure in my paper.
Oh, your paper.
Yeah.
Okay, great. So ask me. Do you want to give like a?
Yeah. So one way to think about it, once Irene talks about the characterization of DA, okay, you'll be able to modify it a little bit by saying that if you rank the school first, then you have the highest priority for that.
That's right, I remember this. Okay, let me answer your question, but after I've talked about the DA characterization, then I'll also briefly mention Nikhil and Paolo's characterization of Boston.
Actually, all school choice mechanisms that are used in practice now have characterizations like that after you think about these two papers and that sort of thing.
So we'll start off with the deferred acceptance characterization. That's kind of going to get us in the right mindset to think about why cutoffs, well, first, what cutoffs are, and second, why cutoffs can characterize these different mechanisms. And then I'll touch on Boston. Okay, so first, let's start with our model. We're going to be using the same large market model in all of today. And so I'm going to define it once for us. So what is this large market model? In this large market, again, we have many students, and we're going to assume that each college has many seats. Okay, so the set of colleges is going to be finite, but the set of students is going to be getting really, really big. And so as the number of students gets really, really big, we can think of them almost as a continuum, right? There's no more individual students anymore. There's just this mass of students. And so that's the approach we're going to take. This kind of approach is, not new. It goes back as early as Alma and perhaps even before that. But in the context of matching, this is going to give us a much nicer way to think about deferred acceptance, and then by extension, all these other mechanisms as well. And so in deferred acceptance, we're going to have this supply and demand characterization. In top trading cycles, we're going to have a trade balance characterization. And this large market is going to allow us to, instead of running the algorithm, we can just kind of define sort of the primitives of this market, and compute in closed form of the market is simple enough what we expect the outcome to be, and also comparative statics of the outcome, which is very useful. Going back to one of the questions yesterday, we're also going to be able to say things about continuity. If we change the market by a little bit, do we expect the outcome to jump or to stay roughly close by? And even though the examples I'm going to show you today are going to be very, very simple markets, in principle, you could use this approach even if there are complex preferences or complex priorities. One example of a slightly more complex priority is like in Boston mechanism, where your priority is actually going to depend on the preference that you're for. So here's our model. I've slightly modified the model. This is not yet a large market model. This is just a model we've been working with. I've slightly modified it for you so that when we switch to the large market, the notation will be consistent. So what have I changed? I still have a finite number of students. Okay, and they're still going to have strict rank ordered preferences over schools. I still have a finite number of schools, which can each admit some quota, Q, of students. And that school is going to have a strict ranking over students, but instead of expressing it that way, I'm going to express it in terms of the student's rank at each school. Okay, so I've introduced this new thing in orange, this R theta at C. Okay, what is R theta at C? It's going to be a number between 0 and 1, and it's going to encode for me the percentile rank of student theta at school C. And so this thing exists even in my finite market. I have 10 students. I'm the second ranked one. I'm going to be at the 10th percentile. And so hopefully this, you can see immediately why this kind of setup is going to be useful if we move to a continuum of students, right? Because I'm just going to keep exactly the same description of the students' preferences and the school's priorities. And the only thing I'm going to change is instead of having a finite set of students, I'm going to have a mass of students. Okay, some distribution of students that tells me for each of these finite number of preference profiles, right, how many of them have what rank at each school. One way I'm going to visualize this for the rest of today, Oh, yes.
When you say the students distribution specified by new set, but isn't it, since it's the ranking, isn't it just like uniformly distributed, or?
Let me give some examples using this visualization. Okay, so here's one way you can visualize what such a distribution could look like. Okay. Before I look at the distribution, let me just introduce this visualization. So here I am showing you one way to visualize things that I'm going to use throughout today's lecture for two schools. On the x-axis, I'm plotting the rank of students at school 1. On the y-axis, I'm plotting the rank of students at school 2. Okay, so if I pick, for example, student theta 1 at the top here, right, they have a very high percentile rank at schools 1 and 2, which means that well, they're kind of in the top right. So that means they're going to be very highly ranked at 1 and very highly ranked at 2. And in addition, I also need to specify the student's preferences. So one way I could do that is just, label the student, their preferences, they prefer school 1 to school 2. Okay, so that's one way I could describe things or understand my distribution visually. A second way is if there's just two schools, there's just two preference profiles, right? Preferring school 1 to school 2 or preferring school 2 to school 1. Okay, so I could just, have a square for each of these, right? On the left is my square for students who prefer school 1 to school 2. On the right is my square for students who prefer school 2 to school 1. Okay, and then what my eta is going to describe, this distribution of students, is where are the students located on these two squares? And so what we're referring to is, let's say I just uniformly at random, draw a lottery number for all the students at all the schools independently, right? Then my distribution is going to be uniform on these two squares. But there could be a lot of other ways that the priorities are set up, right? Let's say I use single type breaking, right? I'm going to use the same lottery at both the schools. That means all my students are going to be on the diagonal. Okay, I don't have an animation for you, but you can kind of picture it. That this is the if I have two squares, something like this. It's going to be multiple tie breaking if all the students were a priori indistinguishable. Something like this is going to be single tie breaking, because if I have high priority at 1, like my number at 1 is going to be the same as my number at 2. Going back to the Boston mechanism, right? If I rank school 1 first, I'm going to have high priority at 1 than if I rank school 2 first. So the Boston mechanism is going to impose a restriction on sort of this distribution. That let's see, if I'm assigned to 1, I have higher priority at 1. If I prefer 1, I have higher priority at 1. If I prefer 2, I have higher priority 2. So something like,
yeah. 1, 2. Only on the right side for this one, and maybe on top half of this one.
I can't overlap.
Oh, yeah. You're right. Negative value.
This one, the positive side. Okay, yeah, I think this is fine.
Yeah.
The students at 1 are going to be sort of further to the right. The students who prefer 1 are going to be further to the right, and the students who prefer 2 are going to be further up. Okay, so these might not be uniform. For example, if it was Right, if it was uniform tie breaking given within those groups, it would look something more like this. But in general, the students in one are kind of going to be here-ish, and the students preferring two are going to be here-ish. Boston with, let's say, okay, so this is kind of a new way to visualize the preferences of students and also their priorities at all the schools. Questions? Yes.
Is this the distribution of the preference or of the reports?
Great question. This is going to be the distribution of their preferences. Well, I guess no. For Boston, this is going to be the distribution of the reports. Yes, but that's why thinking about Boston is a little bit different. For all today, it's going to be equivalent, right? Because the mechanisms are strategy proof, and also your priority is not going to depend on your reported preference. So there's going to be no restriction on what these distributions look like in the squares for today. Yeah, but for Boston, this picture on the left only makes sense if we think about it in terms of the reported preferences rather than the true preferences. And so it'll be a little hard to draw the picture for in terms of true preferences, which is roughly how I'm going to be thinking about these for today, without knowing sort of how people are strategizing. There's another question?
It was the same question.
Yeah.
But in general, if you extend this to more schools, do you have to do this for all the possible quarters?
Yeah, great question. The question was, if we have more schools, are we going to have an exponential number of squares? Yes. Okay, but this is sort of just a way to visualize what's going on. Yeah.
Are we also kind of assuming that every student exhausts the list of schools, or can?
Yes, good question. The question is, are all the students going to find all the schools acceptable? For today, yes, that's not going to be necessary for the results, but just for simplicity, let's think that way today. More questions, comments? Okay, good. So this is the mental picture to have in mind for the rest of today. So now let's go ahead with the first paper, Supply and Demand Framework for Two-Sided Matching Markets. This is Azevedo-Leshno 2016. Again, the main takeaways I want you to have for today are fairly simple. They're that deferred acceptance outcomes can be characterized by cutoffs, and we can find these cutoffs by solving supply and demand equations. So I'm going to illustrate all of this to you in 5 slides using some pictures, and then we'll jump in and see some formal statements. So here's a question for you guys. I have here an economy. I've pictured it the same way as those on the board. I have 2 squares of students. I generated this by generating 500 students who prefer 1 to 2 and 500 who prefer 2 to 1, and then just drawing their priorities at the schools randomly. And so I end up with all these little crosses on the squares. School 1 is going to be more over-demanded because it has fewer seats, only 250 seats compared to school 2, which has 500. And the question is, what is the outcome of deferred acceptance on this economy? Any ideas? It feels a little bit hard to think about, right? Okay, but I'm going to show you, actually it has a very, very nice structure. And I'm going to show you this by drawing in, can you see the colors kind of? I'm going to draw in blue circles, the students who end up assigned to school 1, in green squares, the students who end up assigned to school 2, and in red crosses, the students who end up unassigned. Okay, ready? Okay, so we see some structure here, right? What's going on? You can see there's kind of these 2 blue lines, those are going to be our cutoffs, right? And for the students who prefer one, if they're to the right of this school one cutoff, they're going to be able to go to school one. For the students at school two, if they're above this school two cutoff, they're going to be able to go to school two. Okay, you can see kind of the students in this top right corner have their choice of their favorite school. And the students in this bottom left corner don't have a choice of any school. They're going to end up unassigned. Okay. And so you can kind of see that there's this idea that if you have high enough rank at a school, you're going to have the option to go to that school, and then you just pick your favorite school where you have the option. That's the entire intuition I want you to take away from the next, 20, 30 so minutes. Going back to the supply demand kind of description, you can think of these cutoffs as inducing a demand in exactly the way I just described. The cutoffs tell you which schools you have the option of going to. Given your options, you've picked your favorite school. So for example, in this particular economy, the only students who have a choice are those in this top right corner. Okay? And so I care about how many students end up in that top right corner. That's going to define my demand. Okay, in particular, my demand for school one is going to be this long blue rectangle and this short blue rectangle. And my demand for school two is going to be this wide green rectangle and this narrow green rectangle. Okay. And what is a stable matching going to be? Informally, we'll get there soon formally. Informally, it's going to be, I have demand given cutoffs, and I want to pick the cutoffs so that my demand matches the supply of seats. Okay, so going back to the price idea, right? It's basically the cutoff for school one is going to be the price I need to pay in order to get into school one. Now, my price is not, I'm not literally paying money, I'm paying in priority. How good does my priority need to be at school one in order for me to have the option to go? So I look at my priority, I ask, which schools do I have high enough priority given these prices? And then this induces aggregate demand, and I want aggregate demand to match aggregate supply. So that's the main simplification we're going to make when we characterize the outcomes of deferred acceptance. We're going to characterize stable matchings in terms of these supply-demand equations and show that this is going to pin down our stable matchings for us. One moment. The second simplification I've already talked about is we're going to look at a continuum of agents. And what that's going to help us do is smooth out all these discrete jumps, and we get just these nice lines for the supply and demand curves. Supply is always flat, but for the demand curves. Yes.
So in terms of computing like the equilibrium outcome, can we actually think of it like a Walrasian option where like your endowment is your priority, and, or is it just kind of an analogy?
Yeah. The question was, can we think of arriving at this equilibrium as some kind of Walrasian equilibrium? You start out with an endowment. I would say yes. Why don't you wait with that question for a few slides? I have some pictures which I think have a similar flavor. Okay. So this is the entire intuition for this part of the lecture. We have these supply-demand equations that are going to characterize our stable matchings for us. And we're going to look at everything in a continuum model where everything is smooth and pretty. The results continue to hold even if you're in a discrete model. So just a reminder, what was our continuum model? We have a finite set of schools. Each school can admit some mass now of students. And we have this distribution eta that describes where our students are in these squares. Okay, and you can think of these squares as there's one square for each of the n factorial possible preferences over the n schools. And then we just have like, what are the priorities of the students who have those preferences? So in this model, what is an economy? An economy is going to be, I specify the capacities at each school, and I specify the distribution of students over these squares. And that's going to give me my economy. I'm going to make an assumption on the economies I consider today. The assumption I've written here is that schools and difference curves have measure 0, but actually I'm going to make a slightly stronger assumption. I'm going to make the assumption that the R is actually the real percentile, right? So as I'm moving from here, this line here over, let's start at 0 and I move up a little bit to X, then the number of students in this rectangle is going to be X, or the measure of students in that rectangle is going to be X. And that's going to give me that the indifference curves are measure 0. So let's go back to our definitions from yesterday. In this model, what is a matching? A matching is just going to be actually the same thing. I'm again going to map each student. It has to be now a measurable function, mapping the students to the set of schools. Each student is going to be matched to either a school or the empty set. My feasibility condition is going to look the same, but now instead of looking at the number of students, I have to look at the measure of students. This is the measurable function. And in addition, in this paper, for kind of technical purposes, I'm going to assume something called right continuity. That means if I come at a student from the right, like this, and if I look at the assignment of those students as I'm coming from the right, then if the limit of their assignments is going to be the assignment of that particular student. So basically, like as priorities are getting really, really close, if I have any jumps, they're going to be from the left, not from the right. Just a technical assumption, but I am going to use it at one point today. So that's what a matching is. And now let's define a stable matching. Okay, you guys remember what a stable matching was? You want to give me a one-sentence description of a stable matching?
There's no blocking pairs.
No blocking pairs, great. So this little picture here, the dark navy bear and the yellow bear are a blocking pair, right? They prefer each other to pair match. So how do we describe that in a continuum model? Well, we're again not going to have no blocking pairs, but a blocking pair is going to be the student still has there's a finite set of schools, so it's still there's some they prefer the school to their current assignment. And now for the schools, if you look closely at the math I wrote yesterday, this is going to be the same. The idea is that either the school has space for the student because it didn't meet its quota, or there's some strictly less preferred student who's assigned to the school. And so that means the student should be able to go to that school as well. Okay, some you have to think a little bit about, well, there's still space for the student even if the school is at capacity because each student has measure 0. All the things that happen once you're in a continuum model, but this is going to be our formal definition. You can kick out another student only if they have strictly less priority than you. So that's just recapping all of our definitions from yesterday. What I'm going to do now is introduce some new definitions for supply and demand. So formalize this intuition I gave you before. Okay, so the first thing we need is these cutoffs. And so formally a cutoff is going to, or a vector of cutoffs, is going to be a vector that specifies a minimum score for each school in order for a student to have that school as an option. And so here, for example, my cutoff for school 1 is going to be on the x-axis. My cutoff for school 2 is going to be on the y-axis. Now, what is demand? Demand is going to be for each student. Let's look at the set of schools where the rank of that student is better than the cutoff at that school. Form your set of options, or other language we will use today is this is your budget set. This is a set of schools where your priorities give you enough budget to be able to go to that school. And the students are going to pick their favorite school in their budget set according to their preferences. Okay, so this is going to give the demand of student theta given the cutoffs. And an aggregate demand is just I look, I add up all of these students, and so I look at the measure of students who demand a school given particular cutoffs. So that's my definition of demand. My definition of supply is very, very simple. It's just the number of seats at the school. And now here's the kind of the key condition I need for today. I'm going to need that my cutoffs are market clearing cutoffs. So what is a market clearing cutoff? We'll say a vector of cutoffs is market clearing if the demand given the cutoffs does not exceed the supply. So that's feasibility. And if the cutoff is greater than 0, then I need demand to equal supply. Right? Basically, if you go back to thinking about the price analogy, right? If the price is positive, which means some people can't get in, that means the school needs to be full. Right? If the price is positive, the product is over demand. So those are all the definitions we're going to use to formally state all the intuition I showed you earlier. Any questions or comments? Yes.
I mean, the previous question I was asking was like a better sheet of driven type. And yeah, it seems sort of like it is, but one thing that doesn't hold right is the most for software. Trying to figure out what's the market failure.
The question is, what is the market failure which leads to something like the first welfare theorem not holding? So essentially what's going on here is your endowment, your priority, it can't really be sold to other people. There's no transfers. Right? That's the main thing that means that we're not necessarily going to end up at an efficient outcome. So there's some analogy to competitive equilibrium, but not fully.
Yeah. Does the framework still work if there's transferable utility, like schools can offer different financial aid after giving priority?
Let's say we did matching with transfers. Can we still think about things this way? My intuition is yes. How exactly? My intuition is yes. Let me take the specifics of the question offline.
I think there's maybe one more helpful thing to sort of say about the difference between this and sort of market clearing and first welfare theorem or the whole region things. There's no sense in which consumers are the prices are revealing the marginal rates of substitution between goods.
Right.
Uh,
I mean, there is a little bit.
Okay.
Yeah, not a. There's not like a.
Some marginal conditions might have, the way I see it. That, you know, like your marginal utility for school 1 divided by your margin in school 2 is weighted with price ratios. That's kind of a key thing that helps you for the first welfare theorem, but here don't have those things. That's not what determines these cutoffs.
Right. Yeah. Yeah. So the cutoffs if one school is more preferred to the other school, that's going to go into like demand for one is greater for the other.
And one way to say that the marginal person who's rejected from school 1 need not be roughly indifferent between school 1 and school 2. They might have a strong preference to school 1, but yet they're rejected from school 1. So these marginal conditions are more on the priority of the school side,
Right.
Preferences of the students.
Yes. Yeah. Yeah, a number of differences.
Yeah, but that's one.
Yeah, that's definitely a helpful one. Okay, so let's formally state what the cutoff characterization is. First, given our matchings, we can define cutoffs. Okay, how do we define a cutoff? What we're going to do is we're going to look at the score of the marginal accepted students. So what's the lowest priority of an accepted student? Okay, there might not be a min, but there's always going to be an ins. Okay. Next, given a cutoff, how do we get a matching? I just spent a lot of time describing to you how we get a matching. Precisely, the student are going to be matched to their favorite school out of the schools that they're above the cutoff for. And if we match students in this way, it may be that our cutoffs are way too low and some of the schools have too many students, or maybe that our cutoffs are too high and some of the schools are not filled. Okay, so the dilemma is that this mapping from matchings to cutoffs and cutoffs to matchings is going to take stable matchings into market clearing cutoffs and vice versa. And in fact, it's going to be, these are going to be inverse functions. So if we map you to your stable matching and then we map back to the cutoff, you're going to end up at the same cutoffs. And part of this is using like inf and the continuity of the right thing. Question?
Yeah, so I'm not sure here, the budget constraint in this way of thinking about it implies that you would never, a student would never apply for a school where they would be ranked too low, so to speak, right?
Yeah, so what the budget constraint does is it says the student does not have the option of going to a school where they're ranked too low. Okay, so they're never going to demand that school in the sense that demand is not like the set of schools you submit. Demand is going to be the school you're assigned to.
Yeah, but my question is here, does that kind of imply that all students know all schools will be filled up with students with higher rank, right?
So the students don't need to know their demand. We're kind of implementing this demand in the back end, right? After the students submit their preference list, we draw these pictures with the squares. And then we say, okay, this student, given the preferences submitted, this is their induced demand, given the cutoffs that I've defined. So the question was kind of like, do the students need to know the cutoffs in order to define their demand for us? And the answer is no, they just give us their preferences and we're going to define their demand for them. But if you start thinking about, we raised some questions yesterday about like informational frictions, then maybe we do want to give students these cutoffs ahead of time, right? This is going to give them a sense of which are the schools that they have the option of going to. And so maybe they can restrict their preference collection, information acquisition to that set of schools.
Yeah, but that's my question, right? You could imagine like you have a rank, like you have a lottery ticket that's too low. But if that kind of implies that all the other seats before you will be filled up, right?
Mm-hmm. So this, yeah, what you're saying is that these, if for cutoffs to be market clearing, this is some kind of equilibrium condition. Depends on everyone else's preferences, who is more highly prioritized than you at the particular school that you want to go into. Okay, so you need to know a lot of information in order to determine what these market clearing cutoffs are. Is that?
Yeah.
Okay, but again, the students don't need to know any of this, right? We're thinking of this from the context of the market designer who has collected all the preferences. So let's go back to kind of the wall-raising equilibrium and kind of price description. And let's use it on a continuum version of the economy that I showed you at the beginning. Okay, so here I'm going to have two squares. Half of my students are going to prefer school 1 and half of my students are going to prefer to school 2. And the distribution of students on the squares is just going to be uniform. Okay, think of this as multiple tie breaking. And again, school 1 is going to have less capacity than school 2. Okay, half the capacity. And now let's go ahead and run deferred acceptance on this economy. So remember, what was deferred acceptance? Deferred acceptance was students first apply to their favorite school that has not yet rejected them. So no schools have rejected any students. So here, the dark gray is going to be students who apply to school 1. The light gray is going to be the students who apply to school 2. And the left square is all dark because they all prefer 1. And the right square is all light because they prefer 2. Next, the schools are going to reject the students who are less preferred, but they don't have space for. In this case, school 2 has space for all the students who propose to it, but school 1 only has half that space. Okay, so what they're going to do is they're going to reject that lower prioritized half of students. Let's keep going. Now the students who have been rejected are going to propose again. So these rejected students on this left half of the first square are going to propose to their next favorite school, which is school 2. And what do the schools do? Well, now school 2 has too many students who proposed to it, right? Because we just added this half a mass of students, quarter mass of students. And so school 2 is going to reject the lowest ranked students who applied to it. And so that's moving up the cutoff on the y-axis. So one way you can think about what deferred acceptance is doing is deferred acceptance is starting with all those cutoffs at 0 and then moving them up based on who has applied to the school before. Okay, so we can keep going. Okay, and this process is going to converge to a market clearing cutoff. And why is this? Why does it converge? First, it's monotonic, right? The cutoffs are just going up over time, so it has to converge. Second, let's check market clearing. So demand never exceeds supply. That's going to be true at every step because after the schools have rejected the students, the number of students tentatively assigned to a school at the end of the step is never going to be more than the number of seats at the school. And finally, what happens if the cutoff of the school is greater than 0? Well, that means at some point the school had to have rejected some students. So that means the school is going to be full. So that's the whole intuition for why, if you have a stable matching, you're going to have market clearing cutoffs. Yeah.
So I'm wondering, maybe I missed this. Does this characterization of GH buying some like good things? Like, is it easier to implement versus sort of literally just running the algorithm, or like what like aside from the very centrally nice result? What is
Yeah, great question. What does this description of deferred acceptance do for us? I'm going to cover that in the next 5 minutes. Okay, so let's move away from the characterization and start thinking about, well, why is this characterization useful? Right, first, just let's check that everything I proved yesterday about stable matching still holds with this understanding of stable matchings. We still get existence. In fact, we use the same existence proof that the deferred acceptance algorithm converges to a stable matching. Here, the deferred acceptance is going to converge to market clearing cutoffs. We still get the lattice of stable matchings. The set of market clearing cutoffs is going to be a lattice where you have now that lattice is very clear, right? The way you compare cutoffs is like which cutoffs are lower and higher. And we're still going to have a rural hospitals theorem. This was the theorem where that same set of rural hospitals is going to be sort of undermatched in every single stable matching. Well, here, the measure of students matched to each school is going to be the same given any sort of market clearing cutoff that we start with and assign students using that cutoff. And in addition, the set of students matched to each under-demanded school is going to be the same in all stable matchings as well. That's a part of the rural hospitals theorem I didn't state yesterday, but the set of students that are assigned to each under-demanded school is the same whether we're in the discrete model or the continuum model for these under-demanded schools.
Is there going to be one of those results where, as like the number of students comes to infinity, so the continuum, that there is a unique allocation of the call?
Yeah, great. So there's a question about uniqueness, and another question I thought you were asking there is, as the number of students gets large, is convergence of, large finite economies to the continuum economy. The answer to both is yes. Let's get there in 2 slides.
So, what do you mean by the lattice statement? I think as a rational or some uniqueness result. So there is only one stable matching.
Yes.
So I,
Generically, there's going to be just one stable matching. I'll be more precise about that in a few slides. So everything I said yesterday about like the doctor optimal stable matching versus the hospital optimal stable matching, most of the time it's not going to matter. There's just going to be one stable matching. In practice, this is for continuum markets. For large finite markets, we also often observe a small core. So there's only one stable matching or a very small number. But before we go there, let me start the question of why are cutoffs useful by bringing it back to inference. Why are cutoffs useful? I'm going to point us forward to lecture 16, I think it is. Oh, okay. Oh, a few lectures where we're going to see that these cutoffs are going to be useful for thinking about inference. First, something I need to introduce for you is that I've been talking about schools having strict priorities over students this whole time. But in school choice, schools often have weak priorities. Okay, what I mean is that maybe the school cares about students who have a sibling at a school or who live in the neighborhood of the school, and that's it, right? There's these kind of two characteristics that determine how much the school likes you. And if you have neither a sibling nor live in the neighborhood, then you're kind of indistinguishable from all the other students like you. Okay, so in practice, if this is where the priorities come from, they're going to be these weak priorities rather than strict priorities over all the students. The school's going to have these in different sets. And so what we do is we can generate strict priorities using random tie breaking. I alluded to this already earlier on the board with multiple tie breaking and single tie breaking. What is single tie breaking? Well, first, in all of these random tie breaking, what I'm going to do is I'm going to generate for each student a lottery number uniformly between 0 and 1 at the schools. Single tie breaking says I'm going to generate this number once for each student, and that number will be used at every school. Multiple tie breaking says I'm going to independently draw a new lottery at every school. There's quite a bit of theoretical literature looking at, what is the difference in outcomes if we use single tie breaking versus multiple tie breaking. But for today, here are two definitions of how we might do tie breaking. And then we order the students to get a strict priority ordering. We order them first by priority, and then within each priority class, we're going to order them by their lottery number. Okay, so that's kind of one way to think about what's going on with Boston, right? We order all the students first according to their stated preferences, which is students who prefer 1. I totally drew the squares in the wrong way here. Okay, there we go. That's better. Now this is a subset of this. Okay, good. So the students in this square are all the students who ranked 1 first. So all the students who ranked 1 first are going to be to the right of the students who ranked 2 first. And all the students who ranked 2 first are going to be above the students who ranked 1 first. And then their priority at each of the schools is randomly drawn, so they're going to be uniformly distributed within that priority. Okay, so why is this useful for inference? The main idea is that because we have this lottery, it's going to induce for us a quasi-experiment. Right? What we need to do is kind of correct for the fact that we're not randomly assigning students, we're giving them random priority. And this priority is going to interact with demand and preferences in a way that means that the effect of randomization is not exactly the same for students in different priority groups. What we need to do is back out the propensity score.
So another use of this cutoff structure, which Paul is going to talk about in the next lecture, or maybe the 2 lectures from now, because it tells you the probability that you're going to get into any school if you submit a rank order list of a particular type. And so if you want to think about estimating preferences when it's a manipulable mechanism, Paul will explain how you use this cutoff structure and the probabilities that come out of it to estimate preferences, not just things like treatment effects.
Yeah, so let me give you a bit of a sense with this very simple example where those priorities, how those cutoffs might define the probabilities for us. Okay, so here's a very simple example. I'm just looking at the left square. So all my students are going to prefer school 1 to 2. Let's say school 1 has strict priorities. So the students are already distributed along the x-axis. And school 2 is going to give priority to siblings first. Those are students in dark blue, then neighborhood, and then breaks. And then the white students are those who are neither have a sibling nor live in the neighborhood. And then we're going to break ties randomly amongst those groups. So you can kind of think of it as there's a block of students who have siblings, and then their priorities random there. A block of students who live in the neighborhood and their priorities random there. And then a block of students who have no priority and their lottery's number is random in there. So let's think about which of these students have the option to go to school 2 if my cutoff for school 2 looks like this. Right? If my cutoff for school 2 looks like this, then what's the probability a student has the option of going to school 2? Well, first it's a probability, right? Because you need to be above the cutoff. But because they're this marginal priority class, they could be either above or below the cutoff. Okay. And so the probability they're going to be above the cutoff, given that they live in the neighborhood, is going to be A over A plus B, where A is the height of this upper part of the rectangle, B is the height of the lower part. Okay, so that's going to give you your probability that you have the option. And then are you going to be assigned to school 2? Well, you'll take the option. Remember, all the students in this very simple economy prefer school 1. So they're going to take the option of going to school 2 only if they don't also have school 1 as an option. Okay, so that's going to be all the students in this. Let me do that animation for you again. Okay, it's going to be all the students. Oops, it froze. Okay, all the students to the left of the cutoff for school. Because all the students to the right have the option of going to school 1. They don't care about whether they got into school 2 or not. All the students to the left don't have the option of going to school 1. Okay, so we can, what I wrote on this slide is we can now use these sort of chunkings of students that are defined by the cutoffs to define propensity scores, but we've also already seen that we can use these chunking of students to define probabilities of being assigned as well. So that's one thing the cutoffs are useful for. And you'll see a lot more of this kind of flavor of analysis in the next few lectures. Any questions, comments, thoughts? Okay, so then let's go back to those questions about uniqueness and convergence. I'm just going to put the formal statements up for you, or simplified versions of the formal statements. I'm not going to prove anything. So uniqueness. What Azevedo and Leshno show is that given certain fairly weak conditions, there's going to be a unique stable matching. I haven't put up the full conditions for you. I've just put up 2 examples. Here are the 2 examples. One is if your distribution has full support. So anywhere you are in these squares, the kind of point mass there is, well, the point mass is always going to be 0, but you get what I mean. Okay. So if anywhere you are in this square, there's going to be some students, then it's going to be a unique stable matching. Another sufficient condition is if my demand function, remember this demand is a function of the cutoffs. So as I'm varying these cutoffs, this induced demand function is continuously differentiable, then for all but a measure 0 set of those cutoffs, there's going to be a unique stable matching. So this is the sense in which the chance that you're exactly in that measure zero set where you have many stable matchings is 0 in the continuum model. Actually, I lied a bit. I'm going to do one proof for you by picture for this first result. Okay, so why is there a unique stable outcome if these squares have students everywhere in the squares? Let's suppose for the sake of contradiction that there's actually 2 stable outcomes. So that means there's going to be 2 sets of market clearing cutoffs. And one of them is this P minus defines this cutoffs here, and one of them is P plus defines these cutoffs here. If we think about the set of students who are unassigned under P minus, it's going to be all of them who aren't to the right of cutoff 1 or aren't above cutoff 2. If we think of all the students who are unassigned in P plus, it's again not going to be this much larger square. Okay, and so remember we're in this model where all the students find all the schools acceptable. And so all of a sudden we have more unassigned students under P plus than P minus. But by rural hospitals there, we know that can't be the case. The number of assigned students has to be the same in all stable matchings. Okay, so in the paper, you can read what the regularity condition is that's needed in order for the set of capacities where there is a unique stable matching, set of capacities where there is, yes, the set of capacities where there's a unique stable matching will have measure 0 given those regularity conditions. And the implication for that is, as I mentioned earlier, we kind of expect in general that there's just going to be one stable matching. And that if you have many stable matchings, that actually means you're kind of in like a knife edge situation, where if you go a little bit up in one of the school's capacities or change a small number of students' preferences, you're likely to kind of cascade to either that doctor optimal stable matching or the hospital stable matching and go on from there. So we have these points of discontinuity, but there's not that many of them.
I have a question about the proof.
Yeah.
So in a finite economy, we know that there is a lattice of stable matching.
Yeah.
And I believe there's a lattice on P's
Yes.
as well.
Yes.
So how do I reconcile the intuition that you gave here with that?
So there's going to be a lattice. The lattice could be just 1 point.
Yeah, but suppose it's not a.
If this lattice is not 1 point, that means I cannot have any students in that middle region here. Okay, so or another way to think about it is I kind of drew it like this. This drawing is right. This drawing is requiring the lattice already. So given the lattice, that means I can't have, for example, one cutoff up here and one cutoff down here.
So I see. So the cutoffs don't have a lattice structure.
The cutoffs also have a lattice structure. But that means that my distribution of students is going to be kind of lumpy. There's going to be these L-shaped bits where there are no students. Let me put up for you on the slide the results on continuity and convergence. To talk about continuity and convergence, why we care about this is we kind of care about this. Everything here was for a continuum economy. What about for finite economies? What can we say for them? So first I need to say, well, how do I think about a finite or discrete economy in this continuum setting? There's 2 ways you can think about it. One is just I now allow atoms, okay, so points with positive mass. Another way to think about it is I'm going to expand these points into like little squares. Okay, since there's a finite number of students, I can make sure the squares are non-overlapping, kind of like that. And then I still have all the sort of assumptions before about indifference curves and all of that. I can very easily embed a discrete economy in this continuum model. And then I can say all the same things about this embedded discrete economy, okay? I again can define my mapping M that looks at the assignment and finds the marginal students. And I can again look at my mapping P that takes, oh, it was the other way around. The mapping P looks at the cutoffs and finds the marginal student and says that's going to be my cutoff. And the matching M says given the cutoffs, mapping M says given the cutoffs, this is the students are going to pick their favorite school where they're above the cutoff. So here informally is the result on continuity and convergence. First, let's say I have some economy E that has a unique stable matching. Okay, we said this is almost always the case. Now, if I have a set of discrete economies that converge to this continuum economy, okay, I need to define what I mean by convergence. You can read about it in the paper. Then the stable matchings of those economies are going to converge the stable matching of the continuum economy. And the market clearing cutoffs are also going to converge to those market clearing cutoffs. Moreover, at this point where my economy has a unique stable matching, the stable matching correspondence is going to be continuous. So the stable matching correspondence is these mappings and P. So this is a lot of words. It's not even formal yet. But the takeaway you should get from this is that the results for continuum economies should continue to hold roughly for large finite economies. And also if we were to sample randomly an economy from a given continuum distribution and take a large number of samples. Just to show you kind of the rate of convergence, what I'm showing you is two sets of plots. There's the top set and the bottom set. Top set is, let's say I define a matching two different ways. Way number one is I take the cutoffs given by a continuum economy. Now I'm going to sample discrete economies and actually assign students using the actual stable matching of the sampled economy. Okay, so way one is I assign them using the cutoffs. Way two is I assign them using the running deferred acceptance on the sampled economy. On the top, I'm plotting for you the fraction of students who are mismatched between these two. And the lines are the 90th percentile, the 10th percentile in the middle, the 50th percentile. And you can see if I have 10 schools, and I don't know, like 50 students per school, I'm already, the fraction is already quite small. Right? It's like 5% of students. And as I make the number of schools larger, that error is becoming much, oh, sorry, the fraction is, sorry, no, the fraction is becoming quite small. It's like 10% of students. And as I make that number of colleges larger, that fraction is, getting a little bit smaller than that. Another thing I can look at is how accurate are my cutoffs. I told you that the cutoffs should converge, but how quickly are the cutoffs converging? And again, the same sampling of economies, again, this is going to be the 90th percentile of the cutoff for the schools versus the 10th percentile for the cutoffs of the school versus the 50th percentile. And my continuum economy cutoff is going to be 0.7. Okay, you can see it converges quite quickly as the number of students per college is getting large, even if the number of colleges is quite small. Yes.
If all colleges didn't have the same capacity, how would that look like?
Good question. What if colleges don't have the same capacity? The paper kind of characterizes some kind of speed of convergence. It's like root of the capacity. And so if you have lots of schools, I imagine the cutoff for a school would converge roughly at the rate of the capacity of that school. So the smaller schools kind of see more variance. Okay. So in summary, we have deferred acceptance via cutoffs. And what these cutoffs allow us to do is first, we can solve for them using supply and demand equations. And second, we're going to spend, well, you guys are going to spend quite a bit of time with Paolo and others looking at how this alternative formulation of these mechanisms helps us to think about inference in these settings. In particular, it's going to help us calculate these probabilities of assignment, which we can do all sorts of things with. And the main thing we did was we used a continuum model. And the last results I was showing you there is that actually this continuum model is a reasonable approximation if we have a large market. And it could be large in a couple of different ways. It could be large because we have many schools, or it could be large because we have many students per school. I've gone quite a bit slower than I had anticipated, so we're unfortunately not going to have a break today. Sorry, guys. But feel free to do this during the 15-minute coffee break. The prompt, in case you want to do it, is yesterday you had to get in a group of 3 or 4 and find a fact that is shared by everyone in the group. Today you want to find a different fact for everyone in the group that's unique to them. But let's spend our last 10, 15 minutes or so looking at the second paper on what is the cutoff structure of top trading cycles. I think I'm going to have time just to, again, the first 5 slides are going to kind of proof by picture, show you all you need to know to take away the main takeaways. And then there's sort of the technical analysis that allows us to kind of define things formally in a continuum model is much more involved for top trading cycles. So I had some more pictures to kind of introduce that for you guys, but I think I'm not going to have time for that today. Okay, but feel free to flip through the pictures. Okay, so here are my main takeaways. Again, very simple, 2 sentences. The top trading cycles outcome can be characterized by cutoffs. And these cutoffs are going to solve not supply demand equations, they're going to solve something called trade balance equations. As a reminder, top trading cycles is we have students pointing to their favorite schools, schools pointing to their favorite students. Here we've kind of entered in the middle of the run of top trading cycles, and here's one cycle, and Kyle is pointing to the brown school, Eric is pointing to the yellow school, and they're both part of this cycle, so they'll be assigned to those schools respectively, and we end up with Stan, Kyle, and Eric all assigned to their favorite school. So that's one way you can think about top trading cycles. Let's run this exercise again. Here's a slightly different large economy. Okay, I generated it slightly differently. Now 2/3 of students are going to prefer school 1 to 2. I've also confusingly visualized it differently. All the students are now going to be in one square, but I've marked the student with their preferred school. Okay, students labeled 1 prefer school 1, students labeled 2 prefer school 2. And I generated this by just randomly, uniformly IID drawing their priority at the schools and then dropping them in the square. Okay, same question. What is going to be the outcome of TTC on this economy? We kind of know we have to think in terms of cutoffs. So I'm going to give you a moment to think about this. So I'm going to color the students who are assigned to school 1 in green, assigned to school 2 in blue, and who are unassigned red. So go ahead and color the students for you. Look something like this. Anyone see the cutoffs? Yeah. What do they look like? Kind of draw them in the air for me. Yeah. There's I see some there's a bit of an L shape going on, right? So here are my cutoffs. in particular, I want you to notice this L shape of students on the top right. This L shape over here. All of these students are getting their first choice school. Yeah, really, I should have done the other visualization. It'd be easier to see that way. But you can see here as well that you can kind of verify that all the ones in this L shape are colored green and all the twos are colored blue. Okay, and then this little rectangle, they're all assigned to school 2, whether or not they prefer school 2 first. And then this bottom left rectangle, they're unassigned. Okay, so a couple of takeaways from this picture. First, like deferred acceptance and like, lots of mechanisms out there, like the Boston mechanism, the tough trading cycles assignment can be described using cutoffs, but these cutoffs kind of have a different structure to the deferred acceptance cutoffs. So how are they different? Any ideas? How are they different?
They're not like half planes anymore, but they're.
Yeah, so you're not cutting across the whole plane. There's this, for all of them, I've sort of stopped them. I could have continued them really. I'd stop them more for, to see this L shape easier. Well, another obvious thing is that there's now more than 2 cutoffs. There's 3 cutoffs. In fact, there's 4 cutoffs. It's just 2 of them are degenerate. So that's going to be the general kind of idea we have here. Like if you look at this L shape, this blue shape, and this red shape, there's no way to draw 2 cutoffs to separate out these regions. And so in general, we're going to require n squared, well, half n squared cutoffs, 1 for every pair of schools, but half of them are going to be degenerate. And so you can see we basically have here 2 cutoffs for school 2, and then 2 cutoffs for priority at school 1 that are degenerate. So what is this cutoff characterization? I'm going to give it to you semi-formally. Here's the main result from the paper. The TCC assignment is given by cutoffs. There's going to be cutoffs for every pair of schools. So the cutoffs are P, B, C. And how do the cutoffs determine which schools you have as an option? I'm going to call your set of options your budget set. So when is a school in your budget set? School C is going to be in my budget set if there exists some school B where my rank at B is better than P, B, C. So you can kind of interpret P, B, C as the minimal priority at school B that allows you to trade a seat at school B for a seat at school C. What's the smallest priority you can have at B that you can still use priority at B to trade into C? Now we have 5 minutes to go over small numbers. Okay, so let's think about that intuitively, right? We have these P, B, C. Okay. The subscript B, which you can't see, but let's visualize it, P, B, C. The subscript B is like the school where you need to have priority. And the superscript C is going to be the school you're trying to get into. That's the word. There we go. Thank you, Nikhil. Okay, and so let's just understand what these cutoffs look like think that's all we'll have time for. So what do these cutoffs look like? Here's how we're going to get the cutoffs. First, before I look at the cutoffs, let's look at what the budget sets look like. Okay, so this top L shape is going to have a budget set where they have both the schools in their budget set. This little rectangle is going to have just school 2 in their budget set, and the bottom left is going to have no schools in their budget set. Okay, so how is that defined? Well, I've plotted for you here also those cutoffs. So let's just look at the x-axis. We have P11 and P12. And so it's on the x-axis because you're using your priority at 1. And you're using your priority at 1 to try to trade into school 1 or try to trade into school 2. Okay, so if your priority at 1 is to the right of this cutoff, then that means your rank at school 1 is going to enable you to get into school 1 or to school 2. Right? Whereas for school 2, your priority now, the cutoffs are no longer degenerate. So there's some priority at school 2, which allows you to get into school 2, but not school 1. Right? This middle priority here. Okay, so how we get your final budget set is we look at your budget set that you got from each school, your priority at each school, and then we combine all these budget sets into one mega budget set. Okay, so you can see that these students over here on the top left needed to use their priority at 2. Their priority at 1 was not good enough to get them into either school. And these students to the right here needed to use their priority at 1 to get into school 1. Their priority at 2 was not good enough. And that's why we're getting these L shapes. So for more dimensions, then we're going to get, 3 faces of the cube, or have n minus 1, well, n faces of the n-dimensional hypercube. And then once we have the cutoffs, we have the budget sets, and then students just choose their favorite school in their budget set. So let me make one note on what this means now for calculating the probabilities of assignment. Okay, same example, so I'm not going to go over it again. We have our siblings who are top ranked than neighborhood than everyone else. Let's say the top trading cycles cutoffs look like this. Okay, let's ask again the same question, the probability that students are assigned to school 2. So to think about assignment to school 2, first let's look at the set of students who have the option of going to school 2. That's going to be the slightly larger L shape. L shape is defined by everyone to the right of P12 and everyone above P22. Next, let's look at just students in the neighborhood and let's look at their probabilities. Their probability of having the option of going to school 2, well, it kind of depends on if their priority at 1 as well. Because now all of a sudden the probability can go to 2, doesn't depend just on your priority at 2 because you could trade into it using your priority at 1. Okay, so on the right here, these set of students have high enough priority at 1 to get into either school. So they're all of them, all the students in the neighborhood are in the orange sections. They're all going to have school 2 in their options. But these students to the left of that cutoff, there's going to be some probability. That's, again, A over A plus B, that they have the option of going to school 2. And now actually, for all of them, they're not going to have the option of going to school 1. So if they have the option of going to school 2, they want to go to school 2. So you can start to see how you might use these cutoffs to, again, section off your students. Now you're going to have more sections of students, right? Because you have much more cutoffs to worry about. You need to worry about the marginal students in all those sections. And in addition, the cutoffs are they're not just parallel. The students who are at school 2, you also need to worry about the effect of cutoffs at other schools. This is roughly how you would use these cutoffs. in order to determine probabilities of assignment. And so as with deferred acceptance, we can use the cutoffs to find probabilities of assignment, propensity scores, so on and so forth. And so let me take 2 minutes just to flash some pictures for you. There's going to be a bunch of challenges with defining top trading cycles in the continuum. The main challenge is that how do you point to a top student in a continuum? Right? You have to point at least to a measure zero set of students. And so if I give priority to a set of students, how do I define, what my top cycles are going to be? Okay, so all kinds of problems, you're in continuous time. So how do you even talk about how the algorithm progresses? Like you need to have some kind of continuous time progression of the algorithm now instead of discrete time steps. And so what we're going to do is use something called trade balance equations. What the trade balance equations are going to do is instead of just looking at one cycle, I'm going to look at all the cycles that happen between now and the beginning of the algorithm. I'm going to add up all these cycles, and all these cycles are going to satisfy this trade balance condition, which is the number of students offered a seat by a school up until time t. It's going to be the same as the number of students who are assigned a seat at a school up until time t. Okay, so I have these aggregate trade conditions from time 0 to time t for every t. Now I don't have time to show you what this means, but roughly it means that if I'm now here at time t and I go back to time 0, the students in this L shape are going to have to satisfy some trade balance equations. And that trade balance is actually going to define for me this orange arrow. So to define deferred top trading cycles, what I'm going to do is pretend I'm starting anywhere in the square. Ask what the direction of the orange arrow is if I were to start at that point in the square. Solve for it using the trade balance equations. And now to run TTC, all I need to do is start at the top right corner and follow the arrows. Okay, so I'm solving some kind of differential equation.
So, sorry, Irene, so the question, so this picture is in 2 dimensions?
Yes.
You said an order of n square cutoff.
Yes.
So this kind of gives you one set of cutoffs and then you get another set. Yeah.
Great. So what I'm going to do is I follow that differential equation. Then I'm going to ask, well, when do I stop following the differential equation? I stop following it when the first school fills up. Okay, so let's say the first school fills up here. That means the number of students in this top L shape who want to go to school 1 is equal to the capacity at school 1. So I stop it there. Now I can only assign students to school 2. So now my path can only move in the school 2 direction. So it goes down like that. I keep going until school 2 is filled and it stops there. And so you can see this point here, the L shape defined by the first stopping point is going to be my cutoffs with where 1 is the school you're trading from, 1 is the subscript. And my set of cutoffs defined by the second point is going to be the cutoffs for school 2. And so here you can also see why it's degenerate, right? Because once a school drops out, all of the other cutoffs for that school are just going to stay the same. Okay, so that's kind of proof by picture. Here's how top trading cycles work, and here are the trade balance equations that now are going to define for us a differential equation that we need to solve. Okay, so I've officially gone quite over time, so I'll end this there, but you can look in the paper for more results on uniqueness, convergence, just like in the deferred acceptance setting. And we also have a nice little example using both the deferred acceptance and top trading cycles characterizations to compute welfare for a very simple economy and kind of talk about things. Okay, so that's all I have time to share. Thank you, everyone.